solve a fluid dynamics problem involving wall shear stress. Let's first understand the question. Air with a density of 1.2 kilograms per cubic meter and kinematic viscosity of 1.5 times 10 to the negative fifth square meters per second flows over a flat plate with a free stream velocity of 2 meters per second. The wall shear stress at a location 15 millimeters from the leading edge is tau sub W. What is the wall shear stress at a location 30 millimeters from the leading edge? We're given four options. A, tau sub W over 2. B, square root of 2 times tau sub W. C, 2 times tau sub W. D, tau sub west over square root of 2. Let's visualize this problem. We have a flat plate with air flowing over it. The air is moving from left to right with a free stream velocity of 2 meters per second. We're asked about two specific locations, x1, which is 15 millimeters from the leading edge, and x2, which is 30 millimeters from the leading edge. At both locations, there's a wall shear stress, which we'll denote as tau sub W1 and tau sub W2 respectively. The leading edge is the point where the fluid first contacts the plate. To solve this problem, we need to understand how wall shear stress varies over a flat plate in laminar flow. According to boundary layer theory, for laminar flow over a flat plate, the wall shear stress is given by the expression tau sub W equals 0.332 times rho times u squared times the square root of the kinematic viscosity divided by u times x, where rho is the fluid density, u is the free stream velocity, nu is the kinematic viscosity, x is the distance from the leading edge. This formula can be rearranged to show that tau sub W is proportional to x to the power of -1/2. Let's call the constant part c. So we have tau sub W equals c times x to the power of -1/2. Now, let's apply this formula to our specific problem. At location x1, which is 15 millimeters from the leading edge, the wall shear stress is tau sub W1 equals c times x1 to the power of -1/2. Similarly, at location x2, which is 30 millimeters from the leading edge, the wall shear stress is tau sub W2 equals c times x2 to the power of -1/2. To find our answer, let's take the ratio of these two equations. Tau sub W2 over tau sub W1 equals c times x2 to the power of -1/2, divided by c times x1 to the power of -1/2. The constant c cancels out, giving us tau sub W2 over tau sub W1 equals x1 to the power of 1/2 over x2 to the power of 1/2, which is equivalent to the square root of x1 over x2. Let's substitute the values and calculate the result. We have x1 equals 15 millimeters and x2 equals 30 millimeters. So tau sub W2 over tau sub west 1 equals the square root of 15 over 30, which simplifies to the square root of 1/2. The square root of 1/2 is 1 over the square root of 2. Therefore, tau sub W2 equals tau sub W1 divided by the square root of 2. In other words, tau sub W2 equals tau sub west over square root of 2. Looking at our options, the correct answer is option D, tau sub west over square root of 2. Let's take a moment to understand the physical meaning of our result. As we move further along the flat plate, the boundary layer gets thicker. This means that the velocity gradient at the wall decreases, which in turn means the wall shear stress decreases. Specifically, in laminar flow, the wall shear stress decreases with the square root of the distance from the leading edge. This is why, when we doubled the distance from 15 to 30 millimeters, the shear stress didn't decrease by half, but rather by a factor of 1 over square root of 2, which is approximately 0.71. To summarize, the wall shear stress in laminar flow over a flat plate follows the relationship. Tau sub W is proportional to x to the power of -1/2. When we double the distance from the leading edge, the wall shear stress decreases by a factor of 1 over square root of 2. Therefore, the wall shear stress at 30 millimeters is tau sub west over square root of 2.